Hey guys, Mr. Canistero here. In today's video, we're going to use one of the most important concepts in physics, the work-energy theorem, to derive all the equations for mechanical energy, such as we're going to calculate the kinetic energy, aka the energy associated with an object in motion, the potential energy stored in an object due to being raised up in the air, which we're going to call gravitational potential energy, and by the end of the video, we're also going to calculate the elastic potential energy, aka the energy stored in a spring when you stretch or compress it. So let's go ahead and get rolling. First off, what is the work-energy theorem? In my own words, I really like to think of the work-energy theorem in very simplistic ways. I just simply think as this. When you do work on an object, work simply just changes the energy of an object. AKA, when you do work, you add or take away energy. For example, if you're sitting in your chair right now, you can do this. Take your chair and simply give it a push. When you take any object, like just a chair or a box, and you give it a push and move it, you're doing work. You know that you've given energy because that chair moves away. Similarly, when you push an object like this box on the screen or like your chair, and after you push it, it comes to a stop, like the screen did there, you know that it comes to a stop for a reason, namely typically for this box or your chair, friction brings it to a stop. And what's happening is friction's also doing work, which is taking away energy. In all these cases, though, work changes energy. Written in more formal ways, we just simply say this. The work done, which use the letter W for work, equals the change in energy, which change is represented by the letter delta as in change, Greek delta, and energy E. So simply as an equation, work is the change in energy. Personally, I don't ever think of it as the equation. I just think when I do work on an object, I'm either going to give it energy if I'm doing positive work, or something like friction can do negative work and take energy away from it. So now that we know that work results in some object having a different amount of energy, we can examine things we've done in class where we've done work on objects and examine now not the work done, but the change in energy of the object. So let's go ahead and do that. We'll go back through some examples. The first example is what is the work done when you lift something up? So for example, we did a lab in class where we ran up the stairs. So we took our body weight and we lifted up the stairs of some height. Well, we know that the equation for work in general is simply force times displacement. Well, the force it took to go up those stairs, in order to lift your body up the stairs, you had to overcome your own body weight. And you know that weight is a force, so the work done, at least the force done in this case, was your weight, which is mass times gravity. And the distance that you had to cover, you were working against the force of gravity, and gravity acts in the vertical direction, so we had to consider the vertical distance that you rose, which is the height. And so the distance or displacement was the height. That means the work done in the vertical direction is mgh, weight times height. So because works translate to an increase or decrease in energy, because you did work on yourself to get you up to the top of the stairs, you actually now possess a type of energy. Specifically, you possess what's called potential energy. Specifically, I guess I should say, you possess gravitational potential energy. I'm going to abbreviate with the letter PE for potential energy. Oftentimes we just put a little subscript G there for potential energy. And because of the work-energy theorem, because work results in the change in energy, that means if you did mgh worth of work, you're going to get mgh worth of gravitational potential energy. And so there is our formula for gravitational potential energy. Notice the key variable for increasing or decreasing your potential energy really is the height factor, meaning lifting something up or down, that's what's really going to cause a change in potential energy. Another thing I really like to consider as well is whenever you see the word potential as in potential energy, I really like to associate that word potential with the word stored energy, kind of like an energy is kind of stored inside of you. Because as soon as I jump off those stairs or walk off, I'm going to fall and have moving energy. And so the potential energy allows me to do stuff. That's kind of the big point behind it. The next example, let's consider a spring. So consider pushing or pulling on a spring. When you have some spring and you, for example, maybe pull it, so gets a little bit longer by some amount, x, and the spring had some spring stiffness, k. In the previous video, we showed that the work done, or the work required to stretch a spring, was equal to 1/2 the spring constant, or spring stiffness, times the stretch squared. Well, again, work-energy theorem, that means If it takes 1/2 kx squared worth of work to stretch a spring, it means that I've now stored energy in the spring, and specifically I've stored that much. So the next energy we're going to define is called spring, often called elastic potential energy as well, but spring potential energy. And most often we're going to abbreviate this as potential energy with a subscript S. Every once in a while you'll see it pop up with an E for elastic as well, but in class typically I use the letter S. And again, because work is the change in energy, the potential energy stored in the spring is equal to 1/2 the spring constant times the stretch squared. By the way, if you're curious about where the 1/2 kx squared does come from, you can watch the video on Hooke's law to see where we analyze a graph of force versus stretch and come up with that equation. Finally, the last one we're going to analyze today is we're going to push on an object. So consider like your chair or even the box that I kind of threw around. And when I apply a force or a distance, when I do work on an object and it starts moving, you know that when it's moving, it possesses energy. If you've ever been hit by a baseball being thrown at you, you know that that baseball had energy. You almost felt it. So let's consider the following to help us kind of visualize what's happening and get an idea of how much energy an object has. Consider when I apply like a constant force to an object over a set distance. Let's also consider that the object kind of just is at rest to begin with, meaning it kind of starts from zero. It just makes it easier to think about. It doesn't have to be the case, but it's just easy to think about. When I apply a constant force to an object, the force versus displacement graph looks like that for an object. And one of the things we learned about in class is that the work done on an object is equal to the area of a force versus displacement graph. And for a constant force, that ends up being simply the height times the base, so the work equals the force times displacement. Now, we got to bring back a little bit of our Newton's laws knowledge. Recall from Newton's laws that Newton's second law, F equals ma, if mass isn't changing, force is equal to mass times acceleration. Therefore, the work being done on an object is really equal to, I'll write it over here on the side, the work being done on an object is equal to mass times acceleration times displacement. And so that's one way of actually solving for the work done on an object. What we're going to do, though, is kind of take this one step further to get a more familiar equation to work with. If you're under a constant force, then you're also going to be under a constant acceleration. And we learned in kinematics that if you're under a constant acceleration, you can use what are called the kinematics equations to solve for the motion of an object. We're going to use one of those here to derive a more useful equation. So the one I'm going to use is the equation final velocity squared equals initial velocity squared plus 2 acceleration times displacement. And recall that we started with this problem saying, let's just consider the object at rest. It just makes it easier to think about. So if that's the case, the initial velocity is just 0. And so really, we can just say the velocity at any point in time is just really equal to 2 times the velocity squared at any time is really just equal to 2 times the acceleration times the displacement. If we wanted to solve for the acceleration in this equation, we just divide over, and we see that the acceleration is really just the velocity squared divided by 2 times the displacement. Well, now that we have this expression, we're going to go ahead and plug that into here for our work. And when we do so, we see the following happening. The work equals the mass times this whole term, velocity squared divided by 2 times the displacement, times the displacement. Notice how the displacement terms cancel out. And what we're left with is the work equals, after kind of bringing out the half and moving over the squared, 1/2 mass times the velocity of the object squared. So what that means is when I push on an object, when I throw a chair, throw a baseball, and I do work on it, the energy it gained, the moving energy it gained, is equal to 1/2 mass times velocity squared. This type of energy is the energy associated with motion. We're going to go ahead and call this kinetic energy. I'll go ahead and write it out, actually. Kinetic energy. And so kinetic energy, one of the most important energies that we study in Regents and Honors Physics is the energy any object that is in motion possesses. And so written as an equation, the kinetic energy of an object equals 1/2 the mass times the velocity squared. So those 3 types of energy, kinetic energy, spring potential energy, and gravitational potential energy all have to do with everyday objects, springs, balls, objects that can move. These three are all collectively referred to as mechanical forms of energy. Um, as we move on and watch, and if you move on to the next video, you'll see there are many other forms of energy we're going to study in physics and in other classes like chemistry and in science, such as thermal energy, electromagnetic energy, nuclear energy, and even when we talk about atoms and relativity, the mass energy equivalents. But for now, these three are the ones we're going to study in this unit, really analyzing the motion of objects. So hope you guys got three types of energy out, got the equations. Now we're going to start applying them to problems. So that's it for this video. More problems to come. Have a great day, everyone.